Hello and welcome to next lecture in chapter 5 of our comprehensive course on AI ML DS. In previous lecture we talked about measures of central tendency. In this lecture we want to talk about measures of variation or measures of dispersion. First of all, the question arises is why do we even need to bother about them? Isn't knowing only the measures of central tendency enough for a given data set to get a complete feel for that data set, or that means to recognize or understand that data set's nature? Then no. And you can see these examples. Now here there are two data sets. There are black colored data points. They are spread like this, okay, and there are red colored data points. They are spread in this manner. Now the mean of both is same, and I have taken normal distribution for simplicity. That is the bell curve usual. So in that case, median is also at same location as mean. Okay, so both the key measures of central tendency, that is the mean and median for the observations, are at same location. Here, where my cursor is. Okay, one I have shown by black mu and another I have shown by red mu. So both are at same location. So that means as far just by knowing the mean, I don't get any idea that these two data sets are actually different. But the data distribution clearly shows that the data sets are different. And what is the main difference? The main difference is in their spread. For example, on x-axis, it is clearly looking that red data is spread over wider region compared to black data, or at any other level on y-axis also. Here also, red is spread over a bigger area than black. Here also, red is spread over bigger area than black. And conversely, if I see the vertical height, then it is seen that vertical height of thin distribution, that is black distribution, is more compared to the vertical height of this red distribution. Now the question is how to compare this thing that is called spread. So what we do in this kind of case is, suppose this is one data point, say xi, and what we do is we take its difference from its mean. It is a red data point, but red and black both means are at same position. So we find this distance. That is what? Xi minus mu. Okay, mu stands for the sample mean, and then we do square of it. Similarly, we take second data point, third data point, fourth data point, all red, of course. And for all, we find the difference between the dead data point's value and that is xi and mu. And then we put a square on it. Then we do summation of all those squares for a given data set. So for all red points, sigma xi minus mu whole square. And then we divide it by sample mean. That gives me a quantity which is called variance of this red colored data set. Now then, same thing I can do for my black colored data set. Say I can take this, any one observation, say xi again for black color data set. I find its difference from the mean. So this difference, that is xi minus mu. Okay, mu of black data set. However, mu here, that is the mean here for black and red data set, are same. So this is xi minus mu, and then I do square of it. And similar I do for next data set, its difference from the mean, and find a square of it. Then next data point and its difference from the mean, and then I do sigma xi minus mu whole square. So that gives me, and then divided by the sample mean, that is mu. Okay, here I have made some small mistake. It should not be divided by n, but rather I think it should be divided by mu. Okay, so no, it is n only, fine. Okay, then divided by n, and here also it should not be mu but n. Okay, so divide by number of observations. This parameter, this whole parameter, that is called variance of the red data points. Okay, because while calculating that I am considering various red data points, and similarly this whole parameter, this whole parameter, that is called variance of my black data set. Clearly the numerator for the black data set will be less because the difference is xi minus mu, they are less. The points are close to the mean. Here this numerator will be very large because the points are far away from the mean. So for this point, for example, this is the distance. For this point, this is the distance from the mean. So the distances from mean are relatively larger for the red data set compared to black data set. When I find xi minus mu, this will be larger. Okay, so then numerator is larger and denominator for both are same. I am taking that both data set have same number of points. So in that case, what will happen? What will happen is here numerator is larger, so the variance of red data distribution is higher, and that is why we say that data distribution is spread over a larger width compared to variance of black data distribution is less. So then we say that variance, that is that data distribution is spread over smaller width and it is thin and high. Okay, then there is another quantity which is called standard deviation. Standard deviation is nothing but it is square root of variance. Okay, so this variance we have written, if I write in root, then that quantity is called standard deviation. And similarly, if I write this in root, then that quantity is called standard deviation for the black colored data set. Okay, so standard deviation and variance both are measures of spread or measures of dispersion. How dispersed your data is, how much is the spread of data compared to from the mean arithmetic mean. that is given by variance. Now the question is here that why it is a need. Variance alone is not enough. Why there is a need to define a new quantity, standard deviation, by taking square root? Then actually standard deviation is pretty useful because variance will have a unit which is the square of each observation. For example, all these are lengths in meter or height. Say they are height of some person in meter or centimeter, then meter suppose. Then in that case, what will be the unit of xi meter? Xi minus mu arithmetic mean is also certain meter, and then whole square, that will be meter square. This is just a number, so the unit of variance, that is without square root, that unit of variance would be meter square. So that is dimensionally unit wise not consistent. But if I take a square root, then the unit will become standard unit of standard deviation, that is the square root of variance, that will be meter only. So I can say that this point is, say, how many standard deviation away from mean. So someone can say that this point is maybe 3 standard deviation away from mean. So he can write 3 multiplied by standard deviation. Standard deviation can be shown by maybe delta, or some books write another symbol, maybe S. I don't know here what is symbol used. Okay, S. So then 3S. Similarly, this point is squared at say 2 times standard deviation for the red color data set. So now standard deviation gives us a measure by which I can express my how far away my data point is from mean in terms of standard deviation. So I can say that this point is 3 standard deviation away from mean, this point is 2 standard deviation away from mean. So you can see that both data sets, black and red, have same mean. Median is also same for normal distribution. It is also at exactly same point, mean, median, mode, everything will be at same point. But apart from that, still the data distribution is different. And then how to decide? Measures of central tendency are not enough, but we have to find another measure. They are called measures of dispersion. So now let us easily, once this much discussion is done, then the next part will become very easy for you. Okay, because suppose these are 13 observations of heights of some persons in meter, and first we find mu of those observations. That is the mean, arithmetic mean. We know that that is sum of observations, this thing, divided by number of observations, and that gives 1.666. And then we find difference of observation from mean. Sometimes the difference will be negative if the observation is higher than mean, greater than mean. Sometimes the difference will be positive here because observation is 1.80 and the mean is 1.666. So this is the difference of each observation from arithmetic mean. Now we cannot measure sum here, because what will happen, some negative things will cancel some positive things, and unnecessarily we will feel that this sum is less, or that means the deviation is less. But actually deviation on the left side of mean and deviation on the right side of mean, both are ultimately deviations. So what we do is we square it, so that positive remains positive only and negative becomes, when we square it gives a positive value. So we take a square and then we find the sum of all these squared deviations. Okay, so sum of all these square deviation means sigma xi minus mu whole square. So here I can write a line and I can add all these, and that is sigma xi minus mu whole square, and then divide it by n minus 1. Now this we have also discussed earlier, but again, that for sample mean you don't divide by n, but you divide by n minus 1, and for population mean you divide by n only, and that has something to do with a concept called degree of freedom. But we don't want to delve that deep into it. Instead, just remember that sample mean, so we will divide by n minus 1. So when n is 13, so then you can easily find first this sum squared of deviation, that is only the sum of the rightmost column, and then divide by 13 minus 1, 12. Okay, so then that will give me this variance. And we decide that for variance I don't want to write a new symbol. I could have written V or something, but I decide that ultimately we want to define standard deviation only by taking a square root of this variance. Then why make a new symbol for variance? So we write from the beginning, write it as S square. Okay, so this is the variance. But as I said, its unit is meter square. So you take the square root of variance, that parameter is called standard deviation, and that is 0.0927. Okay, so that means that if I want to write there that a point is 1 standard deviation away. Yes, here a point is 2 standard deviation away, this point from the mean, then that means 2 multiplied by this much distance away. And similarly other point is 3 standard deviation away, this point. Okay, so then we will say that it is 3 multiplied by this distance away from arithmetic mean. Now let us take another data set, because I want to actually show you by plotting graph that this discussion which we had done by drawing data points in 2 different regions. Okay, then that discussion I create same another data set which is having different values. So just like that, one red and one black, and this time also I am ensuring that my arithmetic mean remains the same. But so if you find the arithmetic mean of this, that will also be same as the arithmetic mean of previous one. So that is 1.666. Okay, for the second data set also. and if you calculate, then it is 1.666. Sum of observations divided by number of observations. Now then you calculate the variance of each of deviation of each observation from mean. So that means this observation minus mean, second observation minus mean, third observation minus mean. And as I said, if observation is greater than mean, then the answer would be positive. If observation is less than mean, for example, is 1.45 is less than this, then the answer would be negative. So this is, if I do sum of these deviations, I don't get a proper measure, because some positives will cancel some negatives. So I square it and then take square root. So first I square it and then do sum of these. So this is called squared deviation. This is called sum of squared deviation. This much. Sum of squared deviation. Okay. And then I divide it by either n if I am calculating variance for population, or n minus 1 if I am calculating variance for sample. So we have done earlier discussion that mostly we do all calculation for sample only. Population is always very difficult to handle. So then in that case, n minus 1. Now here if I find the sum of these two, then the sum would be totally different, and therefore n minus 1 observations are still 13, so the denominator is 13 minus 1, 12, but the numerator is now different, and therefore the variance is here 0.10496. Earlier what was the variance? If you see, then it was 0.00856. Very less variance was there compared to this case, where the variance is pretty high, and then I can take the square root of that. That is called standard deviation. That is also very high, 0.3247. So that means that here standard deviation was just this much, while here standard deviation is 0.3247. Okay. Now let us plot this data set, just like here I had drawn this data set, but let us now plot using NumPy. Again, the code is here not important at present, because we have not yet learned Matplotlib and PyPlot. As I said in previous lecture, we have kept total 4 or 5 whole chapters on visualization. But I just want to show that these are the same two data sets which I have shown earlier. So data set 1, its variance would be 5, and data set 2, its variance would be 50, and then 15. And then if I plot them, then this. So you can see one plot is very, very wide. This blue colored plot. It is so wide that it is extending almost from the negative side to 100. Okay. And other plot is thin, red colored plot. It is just extending from somewhere around 42 to 60, or more than 60, just more than 60. But the plot which is thin in width, that means less variance, that plot has more height. Okay. And the plot which is high, having more variance, that has less height. You can also find their standard deviation. Then standard deviation for red color is 5, and standard deviation for the blue color, I think that I have not annotated, but that would be, I think 5 it will not be, variance is 5, okay, spread is 5, then there is a variance would be 15, okay. So that is what you are getting. This is the summary of what we have discussed, that this is the formula for population variance, and right side is the formula for sample variance. There is absolutely no difference, just symbols are changed. For population variance we write sigma square, and standard deviation we write its square root, that is sigma, and for sample variation we write s square, and its square root is s. And the other difference is, for population the mean is shown by x bar actually, and for sample it is shown by mu. So here the symbols have to be interchanged, but that is okay. I mean, there are some books which select population mean as mu and sample mean as x bar. The point is just to distinguish and stay consistent throughout the whole book, that one is different from the other. So as soon as student looks at it, he should understand that I'm talking about population or I'm talking about sample. So we will perhaps use the reverse of this. So x bar will be for population and mu will be for sample. Here also x bar will be here population and mu will be for sample. And third difference, first difference is this symbol, second difference is in symbol of the mean, arithmetic mean, and the third difference is whether you divide by total number of observations in entire population or entire sample, or whether you divide by that number minus 1. So for population you divide by only total number, and for sample you divide by that number minus 1. And that has to do with something called degree of freedom, as I said. So somewhere in some plot, I will show you one parameter that takes care of that degree of freedom. Okay, anyway. Now, how to find the measures of variation? One measure of variation is simple, range. Okay, so that is the difference between maximum and minimum value. For example, for the red graph, this is the maximum value and this is the minimum value. So its range is pretty wide, this much. While for black graph, the minimum and maximum values are these two, and therefore its range is smaller. This is the range of black colored data set shown by red color, and this is the range of red colored data set shown by black color. Okay, fine. So that is what it is. Range is very simple. Whatever array is there, maximum minus minimum. So do it that way, and range is 15. Then variance. Variance is the take for variance. Now we don't have to do all this exercise visually or all this exercise which I have shown in this table, that first find mean, then find xi minus mu, then find xi minus mu whole square, and then take the square root and everything, nothing doing. NP numpy has just a function np dot where, and just provide it with two arguments. First argument is data. Data should be passed as a numpy array, so don't pass it as a list, otherwise it will throw error. But data should be passed as a numpy array, and these argument is what I was talking about. If you are calculating population variance, then these arguments should be put to be 0, and in that case, that denominator would become n. And if you are talking about sample variance, then these arguments should be put to be 1, so the denominator would become n minus 1. So you just have to use np dot where your data and how much is the degree of freedom. If you are calculating for population, use degree of freedom 0. For sample, use degree of freedom 1. So here I am getting this is the variance. Then standard deviation is the square root of variance. So you can just find np dot square root. Variance you have already calculated by np dot where. So then the standard deviation is this, okay, for this data set, this particular. And then coefficient of variance. Now this is another term which is nothing but the ratio of standard deviation and the arithmetic mean. Okay, so that parameter is called coefficient of variance, and if you find it, then it comes out to be 0.54. But normally the custom is that coefficient of variance should be expressed in percentage. So I have multiplied by 100, and while printing the result, I have written a percentage symbol. So I'm getting that coefficient of variance in percentage is 54.23. So what is coefficient of variance? It is the ratio of this standard deviation here. It is the ratio of standard deviation and arithmetic mean multiplied by 100, that many percentage. Okay, so that is about coefficient of variance. Now, so we find by code only. That is what I'm saying. NumPy makes things very easy for us. We don't do all this manual calculation and sit with pencil and pen and everything. We just do it this way. Okay. Now, next lecture we will talk about this thing, that is skewness of the data set. So far I have talked about one, measures of central tendency, second, measures of spread or dispersion, but sometimes those two are about the dimension or size of data distribution, but sometimes size alone is not important, data size is important. So measure of central dispersion and measure of central tendency and measure of dispersion are important, but apart from that also something more is required. For example, there may be two data sets which are more or less same spread and even same arithmetic mean also. So this is one data distribution. I am not drawing data points inside, and this is suppose yet another data distribution. Now here there is not much difference between the width of these two data distributions, or even their means are slightly different, but they are still pretty close. Okay, here it is limitation that I cannot draw it very close, but otherwise it is possible that they are even closer than this. So there is not much difference between their arithmetic mean also. Even width wise also both are looking more or less equal. But this data set, the gray, light gray, previous one which I draw first, that is perfect bell curve. That is, as compared to its central line, red line, it is perfectly symmetric on right side and left side. But this red, it is not perfectly symmetric. That you can see that on left side it is a perfect bell curve, but on right side, if it would be perfect bell curve, then it would be somewhat like this. Okay, this is a straight line, but it would be somewhat like this. But instead, it is as if someone has stretched the data distribution towards the positive x-axis. So that is why this red curve, we say that it has a skew. So the question is that is there any way to measure that skew? And similarly, there is another term here, it is written kurtosis. Then is there any way to measure the kurtosis? Then yes, there is a way to measure the skew and the kurtosis also. And there I will not even explain this whole conceptually, that what, just like here I explained variance. It is just enough that kurtosis means like this. This is called, red is skewed towards the right side or positive skew. And similarly, if there is one data distribution this type, then we say that it is skewed towards the, then we say that it is skewed towards left side here. On left side, if someone has just stretched that data distribution, pulled that kind of data. Okay, so it's not perfect symmetric bell curve in short. So this type of data often have skew, kurtosis, and we don't need to bother about their definition, but we have to take care of these things, skew and kurtosis, and then we have to I mean, we can easily calculate by using simple NumPy library only. Again, if I take the same data, that is this, then just the function is very simple, skew of data, and that is not a function of NumPy, but that is again a function of SciPy. Just like earlier, there were two functions. One was G mean, geometric mean, and H mean, that is harmonic mean, and they were not found in NumPy library. But similarly, these are two other functions, kurtosis and skew. They are also not found in NumPy library. They are found in SciPy library. Okay. So G mean and H mean, and similarly skew and kurtosis, they are found in SciPy library. There are formula for finding the skew or kurtosis, okay, and one can calculate by very lengthy calculation by making actual table and then finding the terms and then doing summation and all that, but that is not required. Okay, we don't do things with pencil and pen, but we do the things with code only. So then just a simple import numpy library, import scipy and scipy.state, import these two parameters, and then this is my data. What is its skew and what is its kurtosis? So it says that skew is 0. Now that is because this data set was perfectly symmetric. So the skew is 0. Every time it will not be 0, and sometimes that skew you have to treat. While this kurtosis is here 1.7. So sometimes kurtosis also needs to be treated. So if your data has too much skew or too much kurtosis, then you need to do something. Some operations is done on the data before doing your machine learning modeling, and they are brought within some reasonable range of values. Okay, so this is about this skew and kurtosis. Yes, this is called Pearson's definition. Pearson was a very prominent statistician and data scientist. So Pearson's definition. But similarly, therefore I have written here Fisher is equal to false. Okay, but if you want Fisher's kurtosis, then write Fisher is equal to true. That are just two different ways of calculating kurtosis, and sometimes instead of Pearson, Fisher's kurtosis is used. This is also name of a statistician or data scientist. Okay, so that's where we would like to stop this lecture. Okay.